Hi, John McElroy here, talking all things automotive. Today, we're going to talk about a very interesting technology that can help automakers get to 48-volt systems a whole lot quicker. It's sort of a shortcut to 48-volt. I'm talking with Greg Green here. He's with a company called Vicor that's come up with this thing. But before we even get into that, Greg, why so much interest in 48 volts?
So 48 volts is important because when you look at what you can do with it, it leads to a lot of cost savings, better design, easier assembly, and better use of the electricity in the vehicle.
How so?
Well, I come from the mechanical side of the world, so I always have to reflect back to water. If you think of voltage as pressure and wires as pipes, 48 volt is higher pressure, so you use smaller pipes. What that comes down to in the car is the wire harnesses, the power cables are about 25% of the size they are at 48 volts that they are for 12 volts.
Whoa. They're 25% of the size, meaning they're 75% smaller.
Yes.
So huge reduction in wire size.
Right. Wire size, if you're in the body assembly world, is great because it's easier to route the wires through the vehicle. The other thing it does, which is kind of rare, but not only does it weigh up to 75 or 85% less, but that's 75 to 85% less copper. So it's also less expensive wire harnessing, in addition to being better and smaller. And a lot of times those things don't naturally go together.
Smaller, lighter, cheaper. What's to argue with here, right?
Well, it's a chicken and the egg thing, is that there's 1 to 200 things in a car that use electricity. And they've been optimized since 1964 or so to work in 12 volts. You have 12 volt alternators, you have 12 volt batteries, it's a 12 volt world. The 48 volt is better, but the process of trying to get all of those things converted to 48 volts has been very difficult.
It's never happened. Well, Tesla has made the move, right? Tesla bit the bullet.
Tesla bit the bullet and made the move. And the day after they announced that, thousands of power engineers in the automotive industry went to their bosses and said, this is what I've been talking about. Because what Tesla did is, the details will be pulled out as people like Sandy Munro start to pull the truck apart. But it's a 48 volt main system with local 12 volt circuits, so to speak. So it's called a zonal architecture. So it gives you this mix of the main power runs are 48 volts. You get that weight savings, that cost savings, that ease of routing and assembly. But out where you're at the front of the vehicle and you've got LiDAR sensors and you've got headlights and you've got horns, you can make a local 12 volt run and power those devices.
With your technology.
With our technology, yes.
So, but let's stick on the 12 volt systems. Speaking 48 volt, I remember a lot of engineers talking about going to 48 volt in the 1990s.
Yes.
And it never happened. And I got to believe it never happened because of the cost involved of having to change every single electric motor in a car.
Yeah, if you go through the cost and engineering hours to re-engineer every lamp, every motor, every sensor, every electrical device in the car, from a 12 volt device to a 48 volt device, it's hundreds of thousands of engineering hours and probably millions and millions of dollars in qualification. So you were stuck in this chicken and the egg type thing. People were developing 48 volt compressors because they're just better electrical machines running at the higher voltage. They were smaller, they were more powerful. But you would see a little bit of it in some of the mild hybrids. You would see a 48 volt run because they had a 48 volt starter generator. They could connect a 48 volt compressor to that, but it was very local. So sometimes it's good not to have been in the industry for hundreds of years, and you can just say, well, what if we take as much as we can get right now and then work on the rest? And one of my favorite quotes from the Tesla executives was, now that we've done this, we hope some other people do it because I'd like some folks to add some volume to door actuators and window actuators so we can get those made at 48 volts.
And the industry probably will get there. But in the interim, tell us about your technology, how it can operate with both 48 and 12 volt.
So we've been in this 48 to 12 volt and in high voltage to 48 volt converting business for about 40 years. We've been doing it for high performance computing. We do it for defense applications. We do it for robotics, things like that. And what it is we use a technology called sine amplitude conversion, which is a way in physics of basically stepping voltage from one voltage to another. And then we combine that with our proprietary technology for creating basically silicone-based chip devices to make these, frankly, insanely small. So I have in my pocket 2 kilowatts of 800 to 48 volt conversion.
Let's see this. So, I mean, this is like the size of a matchbox,
Yes.
you know, wood matches,
Right.
right? And it's not very heavy. It's
No.
got some mass to it,
Yeah.
but it's not extremely heavy.
Right.
So what's this do?
So what this does, this would take the power from the battery and step it down to 48 volts. And because the way we do this,
Now, you say step it down.
Right.
You're talking about a traction battery in an electric car?
Yeah, so
stepping it down from
yeah,
that.
right. So in the electric car, you've got a huge cache of electrons at 800 volts because high voltage is best for batteries. It's best for charging. It's best for storage. But you can't run that into the cabin. It's not safe. You have to be under 60 volts to be considered safe. Or what?
From electrocution.
From electrocution.
In case you touch
Right.
something.
Yes. So, if you look in a BEV, you see all these big orange cables, and those are high voltage cables that are clearly marked so no one tries to cut them. So you have to step it down anyways. When you're coming down from 800, the first natural step happens to be 48 volts. And then you get some margin on either side of that. And it's a very comfortable range electrically to step down from 800 down to 48, or from 400 down to 48. And then you could run the 48 throughout the vehicle. We have smaller devices, about a quarter of this size, that will go 1 kilowatt from 48 to 12. So we can take something in the size of an iPhone locally and make a kilowatt of 12 volt power.
So using these devices,
Yeah.
you would just route the 48 volts in the car where
Right.
you wanted that, or 12 volts where
Yes.
you had
Yeah.
it.
And you have choices. The flexibility and the scalability is great because this is 2 kilowatts. If you wanted 4 kilowatts, you put 2 of these side by side. If you wanted 10 kilowatts, we can go 5 of them side by side. And we'll see applications of up to 10 of these in an array.
Now, are they very expensive?
Yes, I can't say we're aiming to be the low-cost supplier. I said how it was great that the 48-volt cables were lighter, smaller, and cheaper. We're lighter and smaller, but it does cost more. But when you do the full balance equation at a vehicle level, it could make sense for you because as you downsize this, you get flexibility. Currently, if you were to look at a 2 kilowatt converter from 800 to 48, it is about the size of a shoebox. And we can do it in about the size of a cigar box. And that's a lot easier to fit in the vehicle because those of us that worked in automotive know that a vehicle is a 10-pound bag with 25 pounds of content. And so space is critical, weight is critical. As you think of the things that bother consumers, range anxiety and charging anxiety kind of go hand in hand. So if you go to 48 volt zonal architecture and you save like 40 pounds by reducing the wires and reducing batteries, you could add 40 pounds to the traction battery and add range. Or, you could use a lighter weight to go farther. If you do the math, you probably would add the batteries. But you're giving the vehicle designer options now to address these consumer pay points. And off the same technology, in something that is about half the size of an iPhone, we can go from 800 to 400 volts, and we can do about 37 kilowatts. If you're wondering at home, going, well, what's that mean? Well, your house generally consumes 5 to 7 kilowatts, and we're talking 37 kilowatts. When you're charging the vehicle, that can go up to 150 kilowatts. And as consumers are buying these vehicles and using them, and people have been putting charging networks out, one of the things that comes up is the first cars made had 400 volt batteries, and then technology improved, they've gone 800 volt batteries. The first chargers were 400 volt chargers. Now the best chargers are 800 volt chargers. So you have this mismatch, and what our technology is really good at is addressing these mismatches. So we can build in something the size of, if you stacked up 4 laptops, we could have 150 kilowatt, 400 to 800 converter. That goes both ways. So we could go from a battery down to 400 volts for a 400 volt traction motor and a 400 volt compressor and things like that. As you have load coming back from regenerative braking, for instance, we can step it back up to the 800 volts to go back in the battery. Because the electrical system in the architecture is very sophisticated. It sounds simple, but it's, you step voltage down to go to things like an active suspension. So you use power and when you want to push the wheels down, you add power, you push them down. When you come on the other side of that and the wheels come up, they make electrons that have to come back in the battery. So one of the important features is that a lot of our devices are what's called bidirectional. So they can work in forward or reverse. They can take the voltage down or they can take the voltage up. And this is you work in more and more elegant and efficient electrical architectures. That's very important.
Now, you said that these things are expensive, but in balance, it might come out to be a wash or so.
Right.
What are some of the other things that are a benefit that offset the cost?
So you've got the weight savings, and depending on the automaker, that's worth anywhere from $5 a kilogram to $50 a kilogram. So that weight savings comes into play. The space savings is important. Our conversion efficiencies are higher. They're at the low end, maybe 95, but generally 96 to 99%. What that means is we throw off less heat, a natural effect of transforming voltage from one level to another level. You throw off some heat in the form of, or waste in the form of heat. We throw off less heat, so your cooling systems can be downsized. You don't have to deal with as much heat. And that's also one of the interesting aspects of a zonal architecture. If you have this shoebox-sized device doing 2 kilowatts of power, it's concentrating all that heat in one spot. If you step down a smaller amount and run 48 volts out to the ends of the vehicle and have 2 smaller devices, you've done 2 things. You've decreased the amount of heat happening at the central point that you have to cool off. And that's transferred to the ends, but the ends, because the voltage change is smaller, there's less heat. So you can actually air cool instead of liquid cool the devices. And when you get into the guts of a BEV, there's a lot of work done on the cooling. The batteries want to be very specific temperature ranges. The power electronics are throwing off heat, and that has to be managed. So being able to make it smaller, more efficient, also optimizes the thermal control system for the battery and the power electronics.
I think one of the things that you guys have used to describe this stepping down from 800 or 400 is you've created a virtual battery.
Yes. This is one of those things that you get to learn as you learn more about electronics, is that the speed at which we can go from no power to full power coming through the device happens at a rate of about 8 million amps per second, which means it is arguably a little bit faster than if you told the battery to start sending you power. So essentially, you could use this as a 48 volt battery instead of having a 20-pound 48 volt battery. And there are some customers that are looking at that and leveraging that to generate the cost savings and the weight savings to justify using the better technology.
And I think if I remember right, you can pull electricity faster out of the 800 volt that you're stepping down than if you had a 48 volt battery.
Yeah, exactly. That's the benefit, is you will get your 48 volt faster at the point of load coming from the 800 volt battery through our device and through the wire harness than if you pull it out of the battery.
Now, Tesla, once they decided to go 48 volts, Elon Musk sent out, all their intellectual property on what they were doing to all the different automakers. Are you finding a bunch of interest in what you've got here now?
Yes, we are. Almost every OEM in every region is looking at how to do a zonal 48 volt architecture. Whether they're using his designs or not, everyone is going into this concept because if you step back and you look at it, you want to get those initial savings. You want, if you can get 80% of the savings with this simple step, you need to go do it, especially because cost of EVs is a big issue. You can say they have a weight issue and they have a cost issue, and this identifies both of those by helping reduce the weight and the overall system cost of a BEV.
So I got to imagine that your technology would allow a legacy automaker to jump in, do a certain amount of 48-volt stuff here, even though some of their suppliers aren't ready. It's sort of a bridge technology until they can bring the rest of their suppliers along.
That is exactly what is happening. You need a bridge to get from where you are to where you want to go. And I don't know if it's people started realizing that not everything in the Cybertruck was 48 volts, or saw enough of the presentations from Vicor and some of our competitors saying, you can run the 48 volt out to the ends of the vehicle and make the 12 volts locally. And between the Cybertruck announcement and some other things, the light bulbs have come on. And so engineers are saying, okay, I now see what I can do. And I'm going to work to make that happen. And this makes it much easier for them because they don't have to build their plan upon having all of the loads in the door 48 volts or all of the loads in the front end module 48 volts. They can have the local 12 volt. And as I said, you can add these to step up power. You can also subtract these as your power needs go down. So as you take some of those 12 volt loads and you convert them to 48 volts and you need less power, you can simply use one less module.
Now, is this a lab sample, or are you guys ready for volume production? If an OEM says, hey, Greg, we love your idea, start shipping.
So we are in the final steps of PPAPing our first 3 products in this 800 to 400.
And PPAP is pre-production.
Pre-production approval process. You have to speak too many acronyms in automotive.
I'm doing this for the audience, but because in automotive lingo, PPAP is very common.
But what that means is we spent the last 3 years building our prototypes, testing our prototypes, putting them through thousands of hours of tests at all temperatures and all power loads. And so these are approved by an OEM for use in their vehicle. And that is happening over this summer. And we'll be working with a lot of customers to test this out and put it into place.
You got any orders yet?
Oh, yes.
Oh, really? So when might we see this in a vehicle?
Late 2025.
Okay, real good.
Yep.
Greg Green, thanks so much for coming in.
You're
Very
welcome.
Interesting technology, because I know 48 volt is red hot.
Yes, it's we're very happy to be here, and we're excited at Vicor to see the 48 volt trend taking off in automotive, because it's something we've actually been advocating for about 8 years, which isn't as long as the power engineers have been, but we've got this point. We're all very happy to see it.